Hello dear friends, welcome to BYJU'S Exam Prep and I welcome all for this particular course, that is GATE PYQ series for computer science students, and today's topic is algorithms. Am I audible? Am I audible to all of you? Can you hear me? All of you can hear me? Hello dear friends. So in today's lecture, we try to discuss GATE PYQs of algorithms. Hello Tushar Sisodia, welcome sir. Okay, and this is about me, myself, Sridhar Dhulipala. Very good evening sir. I am having 20 plus years of teaching experience and I am associated with Byjus from past 1.5 years. We were working on this particular project called Recorded Gate Content, first of its kind. Hi sir, thank you Pranab Paul. And I recorded all these subjects, engineering mathematics for all the branches, discrete mathematics, algorithm, C programming and data structures for computer science students. So you can join my Telegram group, which is CS_Sridhar. You all can join this particular Telegram group for regular updates, notes, the PDF of today's lecture and everything. Okay. So without wasting your time, let me start. And before that, let me tell you about the series which we are conducting for you people. One is GATE PYQ series. This GATE PYQ series, I am presently taking the same session on this particular series only, or in this particular series only, that is algorithms. And on Monday, that is on 2nd, I am coming up with data structures. Not only for computer science students, yeah, today algorithms, graph algorithms, everything will be covered. The PYQs of 2018, 19, 20, 20, 20, 21, 2022, as many problems as possible we try to cover in today's session, right? And even for ECE, electrical and IN students also, we are having this particular PYQ series. And one more breaking news, we are starting this Maha Marathon series, and in these classes you will get revision of concepts, formulae, practice questions and some PYQ discussions also. See, the class duration may go beyond 1.5 hours. Okay, I plan for around 1.5 hours, sir. It may go beyond that also. Let us see as much time as possible, as many questions of GATE PYQs I try to solve in today's session. Got it? So that is the plan of action. And this particular marathon series is going to start from 3rd January. So in this particular marathon series, it is a kind of review. And here we have review of concepts, review of formulae, review of practice questions and review of PYQs. Everything will be done in a big session. So we'll be having full day sessions, almost full day sessions, around 12 days we are planning, sir. It is for EE, EC, IN and CS in the same BYJU'S Exam Prep. Okay, CS, EC, EE and IN channel. Okay. So let us start with our story today. Of course, there is one more mega workshop conducted by DV Sridhar Sir, which is live at 12:30 PM on 1st of January, sir. So let us right away start with problems. Hope you are all ready for the problem, sir. So let me solve the problems. See, assume that multiplying a matrix G1 of dimension P by Q with another matrix G2 of dimension Q into R requires P into Q into R scalar multiplications. We all know this. Computing the product of n matrices G1, G2 and so on Gn can be done by parenthesizing in different ways. So we define Gi into Gi plus 1 as an explicitly computed pair. Here he is giving a special definition for explicitly computing pairs, sir. For a given parenthesization if they are directly multiplied. For example, the matrix multiplication chain G1, G2, G3, G4, G5, G6 using parenthesization G1 into G2, G3 into G4 into G5, G6. Here G2, G3, here in this G2, G3 and this G5, G6, they are called explicitly computed pair, my dear friend. They are called what? Explicitly computed pair, my dear friends. Now we are having a problem. Okay, here we are having how many matrices? 5 matrices, F1, F2, F3, F4, F5, and their orders are also mentioned here. Their orders are mentioned here. Now, in parenthesization of these 5 matrices, we need to tell which explicitly computed pair are present. We don't need the answer, we just need to find out the which explicitly computed pair is present. See, one logic which people use here in this problem is, if you observe Fi, the order of Fi is 1 by 1000. The order of Fi is 1 by 1000. So that may not be, or that cannot be involved in any of the parenthesization. That is, it is the last matrix to be multiplied. So generally what they do for this particular problem as a simplified procedure, what they do is they just multiply F1 to F4. In that, whatever pair comes, that is the answer. Am I clear? So that is how they do it. But let us solve the complete problem for understanding purpose. Okay, let us solve the complete problem. See, earlier I come up with this matrix chain multiplication, even in your GATE AIMER'S series also, where I discuss the problems on matrix chain multiplication. I explained quickly how to solve this problem. Even if it is 5 by 5 even if you are having 5 matrix products also, we can solve it quickly if you can make the observations properly. So let me solve this problem, my dear friends. Now look at this. Now look at this. See, here we start with this, sir. So here I am filling this for you. Initially we fill this with 0, 0, 0, 0. The main diagonal will be filled with 0. Okay, the main diagonal will be filled with 0. Then you just name these fellows like R0, which is 2, R1, which is 25, R2, which is 3, R3, which is 16, R4, which is 1, and R5, which is 1000. So for filling the second diagonal, this top portion will be always filled with 1, 2, 3, 4, 5, or 1, 2, 3, 4 only. This is fixed for the first diagonal. What you need to do is, first 3 numbers you have to multiply, next 3 numbers, like that you can multiply. That is 2 into 25, 50, 53 is 150. So this answer will be 150, sir. Next 3 numbers you have to multiply. So 16 into 25. 16 into 25 is what, sir? 400. 403 is 1200. Next 3 you have to multiply, that is 3 into 16 into 1, that is 48. Next 3 you have to multiply, that is 16,000. So it is 16K, my dear friends. Okay, don't worry. I'll just move so that you can see that last number. Wonderful. We done it beautifully, sir. Now this is for first diagonal. For next diagonal, that is for filling M13. For filling M13, we use this following technique, my dear friends. We use the following technique. Okay, so let me explain that particular technique to you now. The idea is very simple. What we need to do is, see this particular green one. This one plus this one, or this one, or let me put it as dot, plus this one. These two are fixed here. These two are fixed. That is 0 plus 1200. 0 plus 1200. And the other one is 150 plus 0. Now in this case, we have to take 1 and 4 fixed. That is R0 and R3 fixed. That is, we are going to consider 4 numbers in a sequence. And in that, the first one and last one is fixed. And what happens? The intermediate fellow will be changing, like R1, R2. That is, R1 means K value is 1, R2 means K value is 2. So here this 2 into 16 will be fixed, that is 32. And here it is into 25, here it is into 3. And out of these two fellows, this is 32, 3 is what, sir? 96. 150 plus 96 is how much, sir? 150 plus 96 is how much, sir? That is 246. So this value will be 246. We have to take the minimum of these two fellows. Minimum. So the minimum of these two fellows is your M13, my dear friends. Minimum of these two fellows is your M13, my dear friends. The minimum of these fellows is your M13. Obviously, this is minimum. So, K value which you are selecting is 2, my dear friend. The K value which you are selecting is 2, my dear friends. Okay. See, that's what. Okay. For you, Pranab Paul, let me repeat this quickly. See this carefully, sir. It's very, very simple process. See, for filling this second main diagonal, we are going to use the following idea. If you understand the idea, this filling can be done very, very quickly. Pranab Paul, see this carefully. We have to fill M13, M24, M35. See, for M13, we have to take minimum of 2 values. So, the 2 values will be fixed like this, Pranab. They are fixed like this. See, you want to find this value, no? Go to the left corner where you are having 0. This is 0. And immediate bottom fellow, you add these two fellows. That is 0 plus 1200. 0 plus 1200 here. Next value and below value. That is, you have to consider these two values. Add them. 150 plus 0. Now here, in the dynamic programming formulation, we are having the formula Ri minus 1 into Rj. So now we are from 1 to 3 means 0, 3 are fixed here. That is Ri minus 1 and Rj will be fixed and intermediate fellow will be Rk. So Ri minus 1 means this fellow 0 and R3 will be fixed. That is 2 into 16 is fixed. If you want, you can just write down 2 into 16. 2 into 16 is fixed. Once intermediate fellow, you have to use 25 here. And once you have to use intermediate fellow 3 here. Out of these two, whatever is minimum, that you have to select. So which one is simple? Obviously, the second one is minimum. That is the K value which you are going to take is 2, my dear friends. Don't do unnecessarily calculations, my dear friend. This is where people waste their time. You have to identify which one is smaller. That corresponding K you write down, and this value 150 plus 96, that is 246 you write down. Similarly, for M24 also, the story is same. You want to find this. Okay, so let me clear this so that we will not have any trouble here. See, for that what we need to do, sir, the leftmost 0, where is 0 there? That plus this fellow. All of you able to follow? Or shall I come here? And this, sorry, these two ticks and these two dots you have to add, sir. See, that's what I am trying to say, sir. See, this formula which I create means that is the dynamic programming formulation. We are having this particular dynamic programming formulation, sir. This Mij is equal to minimum of Mi k plus mk plus 1j. So with that, instead of doing this particular formulation, I directly observe that for 1-3, obviously what happens, sir? We need to identify that k value. This M1 k value varies from where to where, sir? K value varies from j to, I minus 1 to j. So I minus 1 means what, sir? K value varying from where to where, sir? K value, not I minus 1, K value varies from I to j minus 1. So for M13, this K value will be 1 or 2. That is M11. Hope you understand. So because of that, this value will be added to this value, my dear friends. This value, because M1, I value fixed, then K value is 1. When I value changed, that is I value is 2, K value is what, sir? K value is this one, 3. So we are going to get that particular 1 to 1, then from 2 to 3. Because when you when you have this I to j, you cut it k, k plus 1 to j. I'm sorry, I think I written wrong formula, k plus, yeah, I to k, k plus 1 to j. So that particular formula we are using, my dear friends. Here I and j are fixed. Here I and j are fixed, my dear friends. K value keep on varying, my dear friends. K value keep on varying. Here K value is 1 means 1, 2 you get it. K value 2 means you are going to get what, sir? K value 2 means you get 2, 3, my dear friends. So 1 and 2, that is M11 and M23. So that M11 will be leftmost fellow and M23 will be immediate bottom fellow. Next K value is M12. Then here what happens? M33. This value will be M33. That is 150 and bottommost fellow. So this is how this particular formulation will be continuing. But if you keep on verifying like this, after 1 year you will write the answer, sir. So by observation, I am writing the answers. I am telling you the observation. I am not telling you how to write the formula. Am I clear? I am telling you observation. From the table how to solve the problem, I am trying to tell you. From the table and these numbers you can solve this problem. That method I am trying to tell you. Ultimately, we are using the dynamic programming formulation only. But with the observation technique, I am telling you the solution. If you understand, you can solve the problem faster. That is that. Don't get into formulation, sir. We are automatically using the formulation. So when you want this, you have to do 0 plus 48 is one fellow. 0 plus 48 is one fellow. The other fellow is 1200 plus 0. Now here we are varying from where to where, sir? Here two values are fixed. You know what are the two values which are fixed? R1 and R4 are fixed. That is 25 into 1 is fixed. And K value varies. K value once it is 3 and once it is 16, my dear friends. But out of these two, which one is smaller? See, obviously 1200 is a big fellow. Throw it out. So the smaller fellow is 75 plus 48. 75 plus 48 how much? 78 plus 48. Is it not 123? So if you use this, K value will be, K value will be what, sir? If you use this, K value is 2. If you use this, K value is 3. So you are using two values. So here K value will be 2, my dear friends. K value will be 2. Because K can be either 2 or 3. We are using 2, so we substitute that. Now you understand? See, if you follow this, now you can quickly solve the remaining problem, my dear friends. Now let us see M3. What is the next one? M35. Minimum of. By observation for this fellow. Okay? Now look at this, sir. I am out of the screen. I am filling this fellow. What you need to do? 0 plus 16K, this is useless, so throw it in dustbin. The other one is 48 plus 0. This is important for us. 48 plus 0 is important for us. Are you able to follow? Now look here. For this fellow, the values which are fixed are R2 and R5 are fixed. That is, R2 is 3 and 1000 is fixed. 3 and 1000 are fixed. But what is not fixed, sir? The other one, 16 and 1. Here it is 16 and here it is 1. Obviously, this is smaller, which is 3048. So here we are going to get 3048, my dear friend, and you are using the K value 4. Which value of K you are using, sir? We are using the K value 4, my dear friends. Hope you understand. So this is what happens. Is the idea clear, Babu? Super. Now once you understand, the remaining part is very, very simple, sir. Now the next one. For next one, see what all values you are going to add. One fellow, I'll write it clearly. Like, 14, M14 if you want it. Here we are going to get 3 sums. See, the 3 sums are very simple to identify, sir. According to the formula only, not according to me. See, the 3 sums are like this. You see, for this fellow, this plus this. All of you able to follow? You see this. This plus this, 150 plus 48 and 246 plus 0. And you have to take these three. And here we are going to take at a stretch from R0 to R4. R0 to R4 you are going to take. R0 to R4 you are going to take. And intermediate value K will change as R1, R2, R3. So 2 and 1 are fixed here. So here what are the three sums you are going to get, sir? The three sums we are going to get are 0 plus 123. Next one is 150 plus 48. Next one is 246 plus 0, my dear friends. Now in this, R0 and R4 are fixed. That is 2 into 1 is fixed. Only K value 1, K value 2, K value 3, that's it. K value 1 means 25, K value 2 means 3, K value 3 means 16. Thank you, sir. And that's it. Once you've done it, you are through this. Now, which one is smaller in this? Obviously, the smallest fellow is the first one. 123 plus 50, that is 173. So, the smallest is 173 and the value of K which you selected is 1. The value of K which you selected is first one, that is K is 1 is selected. See, without writing this formula also, if you properly observe, you can solve the problem directly like that also, with the table only, without writing this. But for some people, you need that particular table, so we are completing it. Generally, what happens, then M25 you want. M25 means what, sir? What are the observations for M25? 0 plus 348, then 1200 plus 16K. 16K means 1000, sir. 1200 plus 16K. The next one is 123 plus 0. Here 25 and 1000 are fixed. 25 and 1000 are fixed. So the K value will be either 2, 3, 4. That is 3 here 16 here 1. 3 here 16 here 1. Super, clear. It would be clear, sir. For everyone it would be clear. Sir, it is simple mathematics, sir. You do integration, differentiation. What is there in this? Simple mathematics. Okay? It's a simple algebra work. Nothing more. We are just doing algebra here. It should be much easier. Now what happens in this, which one is smaller? Obviously this is ruled out. And this one is 25,123. So this is smaller. So here K234, K4 is selected here, sir. K4 is selected here. That is smaller. 2500, 123. 25123. 25123. Sorry, 26123, na? Okay, 25,000, sorry. 25123. 25123. Okay, sir. Shall we place all these values quickly now? 0, 0, 0, 0, 0. The next line would be 150, 1200, 48, 60K, 16K, sorry. This would be 1, this would be 2, this would be 3, this would be 4. All of you able to follow? Okay. See, many people do matrix multiplication here. That technique. See, if you are not using dynamic programming, what is the use of recurrences, sir? You have to use it. 246, 123, 246, 123 and 3048. That is 224, 173 and 25123. 1 and 4. Now the final one. Final one we are ready. M15. Final one. Are you ready for final one, sir? The final story. M15. Hope you can do the observations clearly now. Observations are clear now. 0 plus 25123. The next one is 150 plus 3048. The next one 246 plus 16K. The next one 170, sorry, I think 246 plus, I made a mistake. 246 plus 16k, correct only. Last one 173 plus 0. Now here, okay, again this is R0. Just write down these values. R1 25, R2 3, R4 16, sorry, R3 16, R4 1, R5 1000. Here these two fellows are fixed. That is first one and last one. 2 and 1000 are fixed. 2 and 1000 are fixed, my dear friends. Here 2 and 1000 are fixed. Super, super. Now what is fixed? What is not fixed? The intermediate fellow. It may be either 25 or it may be either 3 or it may be either 16. Yeah, it may be 1. Super, sir. So what is the answer? 2173. If you select it, it is K1. If you select second one, it is K2. If you select this, that is K3. If you select this, that is K4. Which value of K you selected? Which K you selected? Which value of K you selected, sir? Which value of K you selected? Done. See, for learning algorithms, we don't need any prerequisites, sir. Basic functions you should know. Little common sense you should have. That's it. Simple mathematics it is. Done. Now, how to divide this? F1, F2, F3, F4, F5. How to divide this? How to divide this? See, first 5 problems today would be very, very interesting, sir. Because I started with dynamic programming problems only today. Dynamic programming, greedy will complete it. Then we'll see asymptotic notation, recurrence relation, then divide and conquer, then graph algorithms. Okay? Like minimal spanning tree, those problems we take up. This is the order in which I am going to continue today's session. Am I clear? First, we do dynamic programming. So, first what we do? We have to divide at what point, sir? F4 you have to divide. F4 you have to divide. That is because 1 to 5 where you are dividing, this will tell you. 1 to 5 where you are dividing, this will tell you. At 4 you are dividing. Now 1 to 4, now it is 1 to 4. 1 to 4 where you are dividing, sir? You are dividing at 1. So the next point would be at F1 we are dividing, sir. F1 we are dividing, that means remaining part is F2, F3, F4, my dear friends. Now next thing is 2 to 4 where you are dividing. 2 to 4 where you are dividing. 2 to 4. 2 to 4 means 2, 4. Where you are dividing, sir? 2 to 4 where you are dividing? You are dividing at 2, my dear friends. You are dividing at 2. So divide at 2. So this is divided at 2. So F1 is done. Next one is divided at F2. Then F3, F4, my dear friends. And finally F4. Done. So you can easily understand the final story here, my dear friends. You can easily understand the final story here, my dear friends. So according to his question, what is that particular pair? Explicitly computed pair. What is that explicitly computed pair, my dear friends? What is that explicitly computed pair, my dear friends? What is that explicitly computed pair, my dear friends? F3, F4. Only F3, F4. There is no other pair, my dear friend. Very good, Pranav. Very, very good. F3, F4 only. Okay, in this F3, F4 is given, but he said F1, F2. That is wrong. Okay, that is the idea. That is the answer for this problem, sir. See, the trick for this problem is, particular problem is, instead of doing the entire work, see, matrix multiplication, 2 matrices we need to multiply, no, Manishka? We have to have 2 matrices, no, for multiplication. If you divide F3, F4 also, you see F3, F4 also, you can do it. What is there in that? It is divided at 3. It is divided at 3. So you get F3, F4. You want, you can go further, 3, 4 also, it will give you direct answer, 3. It can be divided if you want. Don't do F3, F3, sir. For that we don't have anything, because single matrix you don't multiply. It is ready. Single matrix already there. Right. See, what is the short trick which people follow for this problem is, instead of doing full problem, they do only this much. Instead of doing full problem, they only do this much. They only do this much. You understand? So what happens? Your work is reduced. Still you can get the answer because the last matrix is having dimension 1 to 1 by 1000, so that cannot be involved in this. That would be the last one which need to be multiplied, my dear friends. So with that particular order, they just do it. So even from that, you can easily understand in our solution, F5 was already eliminated, separated already. So if you observe it, you can reduce your work for this problem, my dear friends. But I want you to understand the complete story, so that's why I done this entire work. That's why I done this entire work. Very good, Tushar Sisodia. The next problem. The next problem. अच्छा, वो ऑर्डर चाहिए आपको. देखो पहले F2 F3 मल्टीप्लाई होंगे इनसाइड, फिर F2 F3 से, because this part, this is entirely one portion, no? This is how it happens. Okay, let me show you clearly so that you will not have that particular confusion. देखो इधर first we divided it F4, so F5 is the last matrix which need to be multiplied. F5 will play towards the end. Now 1 to 4, in that F1 will be waiting and these three need to be completed first. In that F2 will be waiting, first F3 F4 get multiplied. First F3 F4 get multiplied and F2 multiply with that particular solution. Okay, and that particular solution is multiplied with F1 on the left and this solution is multiplied with F5 on the left. That is the story. That is how this particular multiplication will happen. The next one. Consider the weights and values of items listed below. Note that there are only 1 unit of each item. Only 1 unit of each item is present. See, the task is to pick up a subset of these items such that their total weight is not more than 11 kgs and their total value is maximized. Moreover, no item may be split. No item may be split. The total value of items picked by an optimal algorithm is denoted by VOPT. A greedy algorithm sort the items by their value to the weight ratio in descending order. Value to weight ratio in descending order and packs them greedily, starting from the first item in the order list. So this question is asking the value of VOPT minus V greedy. See, my dear friends, it is knapsack problem. This problem is knapsack problem. Obviously, when you are taking either full item or no, that means it is 0-1 knapsack problem. What problem it is? It is 0-1 knapsack problem. See, for 0-1 knapsack problem, greedy algorithm may not give you optimal solution. So it may work, sir, but it may not give you optimal solution. It may not give you optimal solution. We should note that. So let me give you the solution for this problem, sir. For that, what I do is I just write down the information given. Let me write down information. So we have to arrange the objects according to their profits. And luckily, if you observe, they are arranged according to their profits only. So let me write down the items. First one, second one, third one and fourth one. The profits and weights. So profits are 60, 28. 24, 20 and 24. Okay, I can do 24 and 20. Okay. Then we can go for the next one, last one, that is there. So it is actually, there is a small twist here. 60, 28. Next one is, what is the next one, sir? Yeah, this is 3, sorry, this is 4 and this is 3. Now what about this 10, 7, 4, 2? Now look here, I'll give you a different technique than the tabular technique. For tabular technique, I need to take, 4 by 11 matrix, that is very horrible. So let us take a simple technique than that. Let us take a simple technique than that. That ratio, Vanishka, there are two methods. Here, we have to use both dynamic programming technique as well as greedy technique. And you have to tell the difference between those two. You have to tell the difference between those two. Okay? So let us see this first by dynamic programming technique. Let me tell you the dynamic programming technique for solving this particular problem, sir. See, what we do is, initially, the first item, are you selecting or not selecting? So you are not selecting first item, you call it as 0. So here, the profit is 0, the weight is 0. Suppose if you select the first item, profit is 60 and weight is 10, my dear friends. And here the total capacity is given, sir. Total capacity is 11 grams. That is also very important. Total capacity also we should note, sir, that is total 11, because it should not go beyond that value. Now what you do is, after first item, okay, you may select it or you may not select it. The possible values which you are left are 0, 0, yeah, 60, 10, my dear friends. And you can consider it as, not selecting second item. Only first item selected, second item not selected, then this would be the situation. After selecting first item and not touching the second item, this would be the situation. But after first item and second item both are considered, that is second item selected. After first, second item selected. See, this 0 means the second item not selected. This 1 means the second item selected. So once it is selected, what happens? If it is 0, 0, previous case, when you select second item, it is 0 plus 28, that is 28, 0 plus 7, that is 7, 28, 7 it would be. That is, if it is 0, 0, if you select the second item, the weight would be 0 plus 7, the profit would be 0 plus 28. After this, if you select the second item, the profit would be 60 plus 28, that is 88, and the weight would be 10 plus 7, that is 17. But here there is a problem. Here the cost exceeds total cost 11. So we have to ignore that part, my dear friends. We have to ignore that. So after completing second item, what are the possible things you are having? You may be left with 0, 0, or you may be left with 6, 10, 60, 10. The possibilities 28, 7, my dear friends. You ignore these values which are having capacity more than 11. Now, this is the same situation when you not selected the third item. But after this, if you selected the third item, that is this item is selected, then what is the situation, my dear friends? What will be the situation, my dear friends? 0, 0 and this 24, 4. That is 0 plus 24, profit would be 24. 0 plus 4, that is 4 will be the weight. Suppose after this, if you selected the third item, 60 plus 24, that is 84. 10 plus 4, that is 14. And next one is 28 and 7. Together with this, if you selected the next item, that is 28 plus 24. What is the 28 plus 24, sir? It is 48, 52. And it is 11. So out of these fellows, which are not valid, Babu? This 84, 14 is not valid. 84, 14 is not valid. Throw it out. Got it? Now, after third item, the situation would be something like this. It may be 0, 0, or it may be 60, 10, or it may be 28, 7, yeah, 24, 4, yeah, 52, 11. This is the situation when the fourth item is not selected. What if the fourth item is selected? So, after this, if the fourth item is selected, you just need to add up those values and recalculate what happens here. So it is what happens 0 plus 20, that is 20 and 2, 60, 20, 80 and 12, 28, 20, 48, 9, 24, 20, that is 44 and 6, Then it is 52 plus 20, that is 72, 13. So in this, you can ignore all the fellows whose capacity is more than 11, my dear friends. So now after 4 items are selected, this is the final situation, my dear friends. 0, 0, 60, 10, 28, 7, 24, 4, 52, 11, then 22, 48, 9, 44, 6. Very good. So this is the situation, my dear friends, at this point. This is the situation, my dear friends, at this particular point. Hope you understand. Now, if you observe, in this, what is the highest weight? What is the highest weight possible? What is the highest weight possible? Sorry, highest profit, not weight, sir. Highest profit possible. 60 is the highest profit possible. So that is the story, my dear friend. So the profit is 60 and you use the capacity only 10. And this is the V optimal. So V optimal is 60, my dear friends. That is only this is the optimal solution. That is X1 you taken the full item, X2, X3, X4 you not selected anything. Now what about, okay, greedy technique. What about greedy technique, my dear friends? For greedy technique, we need to know the profit per unit weight. We need to know the profit per unit weight. According to that, we are going to select, my dear friends. We are going to select according to some greedy idea. So let us see that, my dear friends. So here, what is the profit per unit weight ratio? Profit to the unit weight ratio. What is it? Profit to the unit weight ratio. So this is 60 by 10, that is 6. PI by WI is 28 by 7, that is 4. 20 by 4, that is 5. 24 by 2, that is 12. Actually, here itself I will complete it, sir. Why to take extra page? Here itself I complete greedy solution. Greedy solution can be completed here itself. X1, X2, X3, X4. Actually, greedy technique is used for fractional knapsack, but here we are not allowed fractions. We are allowed to take either full item or no item, sir. Either full item ya to no item. Now here if you observe profit is 6. Here if you observe profit is, highest profit is, sorry, 12. Highest profit per unit weight is 12. So 12 means what happens, sir? 12 means weight is 2 kgs. Total capacity is 11. So out of 11, you can reduce 2 kgs. So new weight would be 11 minus 2, 9. So this item number 4 can be selected. So X4 is selected, sir. X4 is selected. Now weight is 9. What is the next profit per unit weight? Highest cost 6. But what is the weight here? 10. But you are having only 9 capacity. So this is not allowed, my dear friends. This is not allowed. That is X1 is not allowed. Then next highest fellow is 5. What is the cost of that? 4. So that is allowed. So 10 is not allowed, but this 4 is allowed. So now the remaining cost would be 9 minus 4, that is 5. 9 minus 4 means 5. So this is actually third one. Third one is selected. Now we are having capacity 5. What about this fellow? This fellow's capacity is 7. You cannot select it. See, even though capacity is there in the bag or knapsack, you cannot select this item because this fellow's cost is more than that. So you can only select X3 and X4, sir. X1 and X2 cannot be selected. X1 and X2 cannot be selected. So what is the answer, sir? X3 profit is what? X3 profit is 20 and X4 profit is 24. So 44 is greedy greedy value. V greedy is 44 and V optimal is 60. So what is the answer for this problem, sir? What is the answer for this? Greedy answer. V optimal is 60 and V greedy is 44. So what is V optimal minus V greedy? 60 minus 44, that is 16. Got it? Is the idea clear? Let us take the next problem, my dear friends. Let us take the next problem. Consider the sequence of 14 elements. Actually, it is a problem under dynamic divide and conquer. But again, we are solving the problem, so I just take it. Consider the sequence of 14 elements, minus 5, minus 10, 6, 3, minus 1, minus 2, 13, 4, minus 9, minus 1, 4, 12, minus 3, 0. See, there is no trick for that, sir. There is no trick for that, sir. We are just arranging according to their profits. Actually, even if you don't arrange also, nothing will happen. In DP, there is nothing like that. You can keep the original order. You can keep the original order also. For DP, there is nothing like that. I just arranged according to profit so that profit fellows will be removed. That is the idea. Actually, in DP, because you have to consider everything, so you don't have to worry about it, sir. Even if you keep the original order also, it works. Even if you keep the original order also, it works, my dear friends. No problem. DP. For DP, there is no problem. Okay? Because whatever fellow is having more cost, those fellows will be eliminated. Ultimately, that is the task here. Now look at this, sir. In this, we need to identify the subsequence having the highest sum. In this, we need to find the subsequence having the highest sum. Of course, there is a dynamic programming approach, sir. In my videos, I given both the techniques for this. Okay. So here what I am going to do is I use cadence algorithm. With cadence algorithm, you can get the answer very, very fast. But the condition for cadence algorithm is at least one positive value should be there. At least one positive value should be there. Then only this cadence algorithm can be used. Am I clear? So here we are going to use two values. One is sum and the other one is answer. One is sum and the other one is answer. Initially both are initialized with a very, very large negative value. Okay, initially both are initialized with a very, very large negative value. That is minus infinity, like that. Then we start with the first fellow. See, here itself I am doing it, sir. Here itself I am doing it. See, here I start with this index. So minus infinity plus 5, minus 5 and minus 5. Obviously, which one is better, sir? Because we need a best sum, higher value. Minus 5 is also better value. So you can directly start with the first value, both. Both answer and sum you can fill that, sir. Both answer and sum you can fill. Directly you can fill both sum and answer. Now, see, this answer will be updated. This answer will be updated only when the current sum value is more than the answer value. Otherwise, sum will be updated, answer will not be updated, sir. Answer will be updated only when the new sum value which is obtained is greater than answer value. Till that point, we just continue the story. So let us see the story, my dear friends. Here the story continues like this. Sum value is minus 5. Now here what happens? We are at this particular index. So the value here, it is minus 10. The present value at this particular position is minus 10. By adding minus 5 to 10, it is minus 5 plus 10. Out of these two fellows, which one is larger? Minus 10 is larger. Yeah, minus 5 plus, minus 5 minus 10. Sorry. Minus 5 minus 10. Which one is larger? Minus 10 is larger. Yeah, minus 5 minus 10 is larger. Which one is larger out of these two fellows? Minus 10 and minus 5 minus 10. Which one is larger, my dear friends? Obviously, minus 10 is larger. So, we are going to use minus 10 as the updated value, and this is ruled out. Now, is minus 10 greater than answer? Is minus 10 greater than answer? No. So, answer is not updated. Only sum is updated, but answer is not updated. Now, next index. Next index value is how much, sir? The value is 6 here. Now, by adding some value, that is minus 10 plus 6 is? Minus 10 plus 6 is 4. Out of 6 and 4, which one is larger? Out of 6 and 4, which one is larger? 6 is larger. So, what we do? We update it with 6. This is not selected, 6 is selected. Now, the current sum value is larger than answer. So, this is updated with 6. Answer is also updated. Now, next position, 3. There the value is 3. By adding some value, 6 plus 3. 3 and 6 plus 3. Which one is larger? 6 plus 3 is larger. See here, either 3 ya to 6 plus 3. Which one is larger? 6 plus 3 is larger. So we update this value with 9. Because this 9 is larger than 6, this is also updated, my dear friends. Next index -1. So current value is -1. This value is -1. And by adding 9, 9 minus 1. Which one is larger? Obviously 9 minus 1, 8 is larger. So you update this with 8. But this is not larger than answer. So answer is not updated. Answer is not updated. Then again next point. Next index. Next index, my dear friends. Here what is this value, sir? -2 and 8 minus 2. What is 8 minus 2, my dear friend? That is 6. 8 minus 2 is 6. And out of this -2 and 6, which one is larger? 6 is larger. So the sum is updated with 6, my dear friends. But 6 is not larger than answer. We keep it as it is. Then next index. We move to the next index, my dear friends. So here the answer is 13. 13 plus 6 is 19, my dear friends. So this is updated because 19 is higher. And 19 is larger than answer also. Here also the value is updated. So you have to continue this process till the end. And the final answer is your answer. So continuing this way, next index. What is that value there? 4. And by adding 19 plus 4, it is 23. Obviously, which one is larger? Which one is larger? 23 is larger. So update this with 23. Here also 23 updated because 23 is larger than 19. The next one, -9. And this value is 23 minus 9. 23 minus 9 is how much, sir? 14. Correct? So 14 and -9, which one is larger? Obviously 14 is larger. So 14, I'm sorry, correct only, 14 is updated. But 14 is not larger than 23. This is not updated, my dear friends. Very good. Next index, -1. -1 ya to, okay, this is cancelled now. 14. 14 minus 1. 14 minus 1 is 13. So this is updated with 13, my dear friends. See, see, it's not like sum is always updated, sir. Sum is always updated with the, see, sum plus current value, yeah, current value. Whatever is larger, that is the new sum value. Sum plus current value, yeah, current value. Out of these two, whatever is larger, that is updated. Am I clear? Answer is updated only when it is larger than the previous sum. See, that's what I'm saying. Here it is the 3 and it is 6 plus 3. Out of 3, 6, 3 cancelled, 9 is updated. Hope you understand. Like that. Now here we are having 13. We are at the next index. See, either I have to use 4 value or I have to use 13 plus 4, that is 17. Out of these two, which one is larger? Out of these two, which one is larger? 17. So this 17 we are going to take it. That is not larger than 23, ignore it. Next index, either 12 ya to 12 plus 17, that is 29. Which one is larger? 29 is larger. So we update 29. Now 29 is larger than 23, update it. Now next index, it is either -3, yeah, 29 minus 3, that is 26. Obviously 26 is larger. Obviously 26 is larger. And next index, 0, either 0 ya to 26. So obviously 26 is larger. Again you write on 26, my dear friends. Okay. Now this is not larger than 29. Problem is done and highest value is 29, sir. So the answer for this problem is 20. Answer for this problem is 29. Hope you understand. Is the idea clear? Dear friends, are you able to follow? Acha, the sequence. See, here you are getting maximum na. From here, you just go up to 29. That would be the sequence. From here, you can identify that. From where you are getting 12, because where it is updated 29, 23. After where you are getting 23, sir, here no, after this. From here, not after this, sir. 23, where you get it first time? Sorry, one second. Where you updated 23? You can see from 29, the previous fellows, 12, 4, 16, 15, minus 9. 15 minus 9 is what, sir? Okay, I think from 13 it will start. Because 13 is updated with that one, that is the value you are going to take. Okay? Hope you understand. You can just see that from 12, 4, minus 1, then minus 9. So what happened? It is 6 up to here, 6 plus 4, 10, 10 plus 3, 10, 23, then it is minus 2, minus 1, then it is 3, then it is 6. So up to here it is 29, my dear friends. Up to here it is 29, my dear friends. The sequence is from 6 it starts, my dear friends. Okay. So from there till what point? Of course, there's a method for that. We'll discuss separately in the next series, my dear friends. See, just adding the previous values, my dear friends. I just added the previous values. From where I got it means just added the previous values till I get the 29. Am I clear? I just added from here. From where the values keep on increasing, I just added. Okay. There is a procedure, separate procedure also for this. We'll discuss later on, my dear friends. Okay. Yeah. The next one. Again, this is another dynamic programming problem. Define Rn to be maximum amount earned by cutting a rod of length n meters into one or more pieces of integers length and selling them. So we are having a rod, we are of length n, and it is divided into one or more pieces of integer length. Okay, then you are selling them. Now Pi denote the selling price of the rod whose length is I meters. So if the length is I meters, the selling price of that particular piece is Pi, my dear friends. Now here this particular sequence is given. Let me write that sequence separately here. Let me write that particular sequence here. Okay. So let me write here 1, P1 it is 1, P2 it is 5, P3 it is 8, P4 it is 9, P5 it is 10, P6 it is 17, P7 it is 18. So this is the piece, okay, length and price of that particular, or I, length and price of that particular length. This is I and this is price of that particular length, my dear friends. Price of that particular length, my dear friends. Now let us solve this problem. See, actually what is happening, sir, we are having the rod of length 1, yeah, rod of length 2, rod of length 3, rod of length 4, rod of length 5, rod of length 6, rod of length 7. So here the question is about R7. The question is about R7. So first of all, let us generally understand. Suppose if rod of length 1, what is the price, sir? Length 1, there is only one price, it is 1. Now if it is rod of length 2, how can you make that rod of length 2, sir? By taking two 1 meter rods or by taking the rod of length 2 directly. So it can be 1 plus 1, ya to 2. 2 plus 0 I am writing, but 2 only. So 1 plus 1, when you take it, the price would be, the cost of rod of length 1 is 1 Another rod of length 1 is 1. 1 plus 1, the price here would be 2. But if you take directly rod of length 2, the price would be 5, my dear friends. Now for rod of length 3, what is the story, my dear friends? For rod of length 3, how it can be made? It can be made like 1 plus 1 plus 1, or it can be made like 2 plus 1, or it can be made like, okay, 3 plus 0, like that we can make it. So out of these, which one is the best price? That is the question now. We have to find the best price, my dear friends. Am I clear? We have to find the best price or the highest price, my dear friends. The one which is giving highest price, you have to find it. See, for this, hold on one second, where it is gone? Yeah. So for this, we can use this simple greedy, not greedy technique, dynamic programming technique. Assume it is a box. Otherwise, let me clearly draw once again. Length 0, length 1, length 2, length 3, length 4, length 5, length 6, length 7. Now suppose if you want length n, sir, general formula I am saying. Length 1 if you want, current length, or suppose you already used a length pi, pi length you used, profit at ith length you used. Plus, what is the remaining length you are going to use, sir? N minus I length. You need the cost for n minus I length. Suppose total length you want n. If you suppose you used a length, say I length you used, remaining length must be what, sir? N minus I length. But here this I, do you know? Do you know what is this I? We do not know. So what we do, out of all possible i's, that is for I is equal to 1 to n, you find all i's. And whatever is giving the best price, that you are going to select it. Whatever is going to give you the best price, that you are going to select it. So you are going to put, for example, if you want to find R3, for example, if you want to find R3, what you need to do, sir? You have to do P, okay, P1 and cost for R2, P2 plus cost for R1, and P3 plus cost for R0. Now R0 is not there now, so let us define R0 as 0, my dear friends. R0 can be defined because it's a recursive formulation. Now we can define R0 as 0, my dear friends. R0 as 0 we can define it. So with this what happens? R0 is 0 means P3 plus R0. What is P3? P3 cost is what, sir? 8. 8 plus 0. And P2 plus R1. See, for R1 best cost separately we already calculated. P2 is what, sir? P2 is 5 plus R1. P1 is what, sir? 1 plus cost for R2. Cost for R2 is 5. Out of these, which one is better, sir? 8 is better. So you are going to take that particular value 8. But every time this much work, we don't have to do it. If you can store the values, you can reuse it, sir. You can store the values and you can reuse it, my dear friends. Okay, so for that what we do is we use the following simple technique. See this. When you want for 1, 1 plus 0, what you are doing? 1 plus 0 directly, that is 1. So that particular value for R1 it is directly 1. You can directly put the profit, my dear friend, no problem. And for this, what you are going to do? For R2, what you are going to do is 5 plus 0 and 1 plus 1. See this crisscross. Here we have 1 5 and the cost values na 5 0 and 1 1. 5 plus 0 and 1 plus 1. Which one is highest? 5 is highest. Put that particular value. Now at R3 if you want. See here it is like 1 5 8 values and here it is 0 1 5 values. Just do this. 8 0. Am I clear? You are just going like this. 5 1 and 1 5. 8 0, 5 5 and 1 5. Which one is larger? 8 0 is larger. 8 plus 0 is larger. That you are going to get. Now at this particular point, see the 4 points 1 5 8 9 0 1 5 8. See for this you are going to take this one. For the next one you are going to take the next one. For the next one you are going to take the next one. For the last one you are going to take this. Of course the same formulation, only by observation technique I am solving it. So it is 9 plus 0 9. It is 8 plus 1 9. It is 5 plus 5 10. It is 8 plus 1 9. Which one is larger? 10 is larger. 10 is larger, my dear friends. The next one. Next one at here. So you already see that 10 plus 0. Its next one is, I'm writing here 1, 5, 8, 9, 10. Here 0, 1, 5, 8, 10. So 10 plus 0 is 10. 9 plus 1 is 10. 8 plus 5 is 13. 8 plus 5 is 13. And 1 plus 10 is 11. So which one is larger? 13 is larger. 13 is larger. Am I clear? Next one. Again, next 6 fellows you take it. 17 plus 0, 17. Where I should write? In the next slide. I think we are exhausted with the slide. No problem. Somewhere I'll put this. I'll write it here. 1, 5, 8, 9, 10, 17, 0, 1, 5, 8, 10, 13. So 17 plus 10, 0, 17, 10 plus 1, 11, 9 plus 5, 14, 8 plus 8, 16, 5 plus 10 is 15, 13 plus 1 is 14. Highest cost is 17. Highest cost is 17. Now the last one. So this entire thing and this entire thing. 18 plus 0, 18. 17 plus 1, 18. 10 plus 5, 15. 9 plus 8, 17. 8 plus 10, 18. 5 plus 13, 18. 17 plus 1, 18. Highest cost is 18. So what is the value of R7, my dear friends? What is the value of R7, my dear friends? R7 value is 18. So R7 19 is wrong. Now here if you observe, there are two more options given. He says R7 cannot be achieved by a solution consisting of 3 pieces. R7 cannot be obtained by a solution consisting of 3 pieces. Of course, if you keep track of the 3 solutions, you can easily write down that, my dear friends. Actually, it can be obtained by a solution consisting of 3 pieces, sir. You can get that 18 by sum of 3 pieces, my dear friends, very easily. Okay, the 3 pieces can be like 18. See, there are different ways you are getting 18. Actually, you are getting 18 by different ways you are getting. See, for this it is 18 plus 0, that is single piece only. Here, if you are getting it means it is 17 plus 1, 2 pieces. If you are getting 18 here, if you are getting 18 here means how you are going to get, sir? 3 pieces. This 3, how you are getting this 3 sum, sir? You have to see 3 sum how you are getting. 3 sum how you are getting, sir? That is 8, how you are going to get 3 sum? It is with a single piece only. But this 18 how you are getting, this 18 how you are getting, sir? This is with this particular 18 sum how you get it. I think it is 13 plus 5. 13 plus 5, and this 5 sum how you are getting, sir? I think it is with single piece. Now what about this 18 sum, sir? What are the 3 sums which are giving 18 sum, sir? Can you please tell me what are the 3 sums which are going to give you 18 sum here? That is 3 pieces giving 18 sum. Can you please tell me what are the 3 pieces which are giving 18 sum here? I think what are the 3 pieces whose sum is 18? Can you please give me that? So we are seeing the cost, not sorry, we are seeing the cost, the length. We have to see the length, sorry. We have to see the length, sorry. The fellows 2, 2 and, yeah, 2, 2, 2, 2 and 3. Yeah, 2, 2 and 3. 2, 2 and 3. Yes, Pranab. 2, 2 and 3. 2, 2 and 3 we have to do it. 2, 2 and 3. Yes, that is going to give you that 18, my dear friends. That is going to give you that 18. So because with 3 pieces you can get this answer. So this is right, wrong answer. And R7 achieved by 3 different solutions. Actually, you can have more than 3 solutions. So obviously, it can be obtained by 3 different solutions is correct answer. So here C and D options are correct, my dear friends. Here C and D options are correct, my dear friends. Here C and D options are correct. Is the idea clear? Yes or no? Okay, the next one, it's a simple Huffman coding problem, sir. Very simple problem. I think you all know what is Huffman coding. Okay. See, look at this problem, sir. Consider the string ABB. Consider the string A, BB, CC, DD, triple E. Each letter in the string must be assigned a binary code satisfying the following properties. That is, for any two letters, the code assigned to one letter must be a prefix of the code assigned to the other code. For any two letters of the same frequency, the letter which occurs earlier in the dictionary order is assigned a code whose length is at most the length of the code assigned to the other letter. So it's same as your Huffman coding problem only, sir. So just let us create the Huffman code for this. You are going to get the required answer for this. So what is it? A. So if you directly see this here, A having frequency 1, B having frequency 2, C having frequency 2, D is having frequency 2, and E is having frequency 3. Just create the Huffman code, my dear friends. Starting with A, starting with small fellows. So first small fellow 1, which is A. The next small fellow is 2, which is B. You combine them into 1. When you combine them, you are going to create circled fellow, which is 3. Now again, you try to arrange them because these two are done. Now we are left with 2, 2. The next one is 3. See, this 2 we can call it as C, this 2 we can call it as D, and this is E, and the circled one is created fellow. See, original fellows are the square leaves. The created ones are internal vertices. Internal vertices for the tree, my dear friends. Now you can combine these two to form 4. You can combine these two to form 4, my dear friends. Good evening, sir. Got it? Very good evening. Now again, let us arrange them in the correct order. 3, then the created vertex, and again created vertex. Now these two can be combined to form 6, my dear friends. Now again put them in the correct order, that is 4 and 6. So 4 is the smallest, 6 is the largest. When you combine that, you are going to get the created vertex 10. So your Huffman coding will be like this, sir. We start with the top, that is 10, whose left child is 4 and right child is 6, my dear friends. 4 and 6 both are internal vertices. 4 and 6 are both internal vertices. Now how this 4 is created, sir? 4 is created with 2 and 2, which are leaves. So it is C and it is D, my dear friends. Then 6 is created with what? The leaf node 3 and this particular vertex 3. Then after this, what happens? This 3 is created how, sir? This 3 is created with leaf node 1 and leaf node 2. Okay, so now we are having name for every fellow. This leaf node is E, this leaf node 1 A, and the second leaf node 2 is B, my dear friends. Now you can give the labels for the edges. Left labels you can call them as zeros, right labels you can call them as ones. 0, 1, 0, 1, like that. So now if you want to know among the set of binary code assignments which satisfy the above two properties, what is the minimum length of encoded string? See, once you write the Huffman code, if you want to find the minimum length of the encoded code, you just see the circles. Circles means the created nodes are there, no? Some of those values you do it, that is the minimum length of the encoded string. Minimum length of encoded string. That would be 10 plus 4 plus 6 plus 3, which is 23. Yeah, you can do that, length of the string multiplied with the frequency, sum of that also. That is sigma depth multiplied with the frequency over all the, all the letters you can do it. That way also you can get the minimum encoded string, my dear friends. Hope you understand. So the answer for this is 23. Hope you all followed this. Is the idea clear? Yes, sir. Now, so these are the problems. There may be some problems may be little lengthy, but once you practice, I don't think these problems are difficult, my dear friends. So they look little dangerous because for first time you are solving, it may take a little time, but once you understand the observation, these problems are very, very simple, my dear friends. These problems may look little lengthy, but if you follow this observation, it is very, very simple, my dear friends. Now let us take up some problems. These are our regular questions, sir, simple problems. Okay, we need to see the correct order of the functions. Please try the answer for this problem, sir. You might have already done that. Try this problem. Try this problem. Try this problem. All of you. Or try this problem. So you are getting feeling like digital board. Some people are worried about the digital board, sir. Okay. So here you can get the feeling of digital board also. Right? Nice. Now if you observe, let us take F1 and F2. Let us take F1, F2, sir. Now what is it? F1 is 10 power n. F2 is n power log n. What you do is you apply log on both sides. You apply log on both sides. Apply log. So when you apply log, what happens? This is n log 10 and this is log n into log n. So this is n and it is log n whole square. But you know that n is asymptotically larger than log n whole square. N is asymptotically greater than log n whole square. That means log F2 is smaller than log F1. That means F2 is smaller than F1, my dear friends. F2 is smaller than F1. So this relation you got it. One relation you got it. Hope you understand. F2 is smaller than F1, you got it. Now you have one more fellow, that is F3. Now we have to, because smaller fellow is which one, sir? Which one is smaller fellow? F2 is smaller. So let us compare F2 with F3. F2 is n power log n. N power log n. And F3 is n power n. N power root n. Again apply log on both sides. When you apply log on both sides, this is log n whole square, we already seen. But this is root n into log n. Root n into log n. Correct or not? Root n into log n. So which one is smaller here, sir? Root n into log n, which one is smaller here? Log n whole square, yeah, root n into log n. Suppose if you cancel one log n, it is log n and it is root n. So still, obviously, F2 will be asymptotically smaller than F3 and F2 is asymptotically smaller than F1 also. Now we are having a headache situation because F2 is smaller than both the fellows. Now which one need to be fighting? F3 and F1 should fight, my dear friends. F1 and F3 should fight. So let us conduct a war between F1 and F3. F1 is what, sir? F1 is 10 power n. F3 is n power root n. Again apply log. So this is n log 10 and it is root n log n, my dear friends. That is n into root n log n. See, n can be written as root n into root n and it is root n log n, my dear friends. One root n cancels, so you get root n and here it is log n. So obviously root n is larger than log n. Root n is larger than log n. That means F1 is asymptotically larger than F3. F1 is asymptotically larger than F3. So we got F2 asymptotically smaller than F1, which is, F2 asymptotically smaller than F3 and F3 is asymptotically smaller than F1. So F2 smaller than F3 smaller than F1, my dear friends. Of course, there is one more way of doing it. Apply log to all of them at a time. So it becomes n. The second one become log n whole square. The third one become root n log n. So common factors. So obviously you can observe that log n whole square is the smallest of all. So log n whole square will be the smallest of all. So it would be to one side. Now you just need to compare these two. In this, root n is the common factor. If you remove it, root n log n, obviously which one is larger? Obviously root n log n, this is larger. That is, this n is larger and root n log n will come here. So this is your f3, this is your f1, and this is your f2. f2, f3, f1, my friends. So at a time also you can do the comparison, sir. If you can do it, otherwise you can take two at a time. Happily do it. Happily observe it and solve the problem. Next question. A recent GATE question. Interesting one. Which one of the following statement is true for all positive functions fn? Which one of the following statement is true for all positive functions fn? See, in some options he clearly mentioned what is the function also. In some options function is not mentioned. Actually, he's kind of giving you hint to solve this problem. He's kind of giving hint to solve this particular problem in the problem itself. He's asking you to consider polynomial, exponential, and one more function which you can consider is logarithm. If you can consider these three functions, this problem can be handled, my dear friends. If you can take these three functions, this problem can be easily handled. Okay. So let us take the first problem. Here fn is a polynomial. You can take any polynomial of degree, say n power k, a polynomial of degree n power k. What if I do fn square? Fn square is n square whole power k, but that can be written as n power k whole square, my dear friends. That can be written as n power k whole square. But n power k is what, sir? Fn whole square. That means fn square is same as fn whole square, my dear friends. That means they are of same order of growth. They are of same order of growth. So option A is true. Option A is true, my dear friends. Option A is true, my dear friends. Now let us see B option. See, if you consider same polynomial, when two functions are of same order of growth, you cannot have one function asymptotically smaller than other function. So option B readily fails. Option B readily fails with the same example. If you take fn polynomial, what actually happens is fn square is having same order of growth as fn whole square. Therefore, if you want to say that fn square, if you want to say that fn whole square is asymptotically smaller than fn square is wrong because of the same example. So when you prove first option, second option obviously fails because here function is not specified. He not specified whether it is a logarithmic function, polynomial function or exponential function. Nothing is mentioned. I take polynomial function. There it fails badly. So option B is false. Now what about option C? In option C, he clearly mentioned what type of function it is. In option C, he mentioned that it is a exponential function. You can take any general exponential function, sir. You can take any general exponential function a power. You can take any exponential function a power n, my dear friends. Okay. So, or b power n, whatever it is. Then what happens to fn square, sir? Fn square will be what, sir? A power n square. Now what happens to fn whole square, sir? Fn whole square will be a power n whole square, which is a power 2n. Are they equal? A power n square and a power 2n, are they equal? They are not equal. So fn square obviously is asymptotically larger than fn whole square. This fellow is larger than a power 2n, my dear friends. A power n square, because n square is larger than 2n, therefore fn square is asymptotically larger than fn whole square, my dear friend. But what he given? Fn, for fn square is having this fn square as he given reverse. He asked, he is saying that fn square is smaller than fn whole square, he is saying that. This is given. When you say fn square is big O of fn whole square means this is what he said, which is wrong. Which is wrong for polynomial function. For polynomial function, that is wrong. For polynomial function, that is wrong. Okay? Sorry, not polynomial, sorry, exponential function. For exponential function, that is wrong. It's exponential, na? For exponential function, this is wrong. So, this option is false. Now, D is also false, sir. Because unless or until you don't know whether it is polynomial, exponential, without knowing the function, you cannot say fn square and fn whole square. See, for D, if you consider logarithmic function, if you observe, consider this, fn as logarithmic function, sir. Log n you consider. Then what is fn square, sir? It would be log n square. That is 2 log n. Then what is fn whole square, sir? Fn whole square will be log n whole square. Obviously, you know that fn square is asymptotically smaller than fn whole square. Fn square is asymptotically smaller than, so this is smaller, but here you are saying this fn whole square is, what is it? Fn whole square is what? Lower bound for this. Fn whole square is lower bound, but fn whole square is upper bound in this case. You are saying it is lower bound, that is wrong. Okay, so here saying fn square is asymptotically large, because when you say big omega means what, sir? What do you mean by big omega, sir? This fellow is having that, see, this function is lower bound. See, when it is big omega means lower bound, asymptotic, tight lower bound. So fn whole square is lower bound, that is wrong. So D option is false. D option is false. Hope you understand, sir. Hope you understand. Is the idea clear, Babu? All of you able to follow? Yes or no? Clear. Very good. Like that. So, in this example, he clearly given you hint also. He asks you to consider one polynomial function, one exponential function, one logarithmic. Then obviously you can get counter examples for wrong fellows. Option A is the only fellow which is correct. Remaining all fellows will badly fail. That is the truth. This is a direct gate question. Of course, all are gate questions only. We are solving gate questions only. So please tell me about this. Please tell me about this. For constant a greater than or equal to 1, b greater than 1, consider the following recurrence defined to be Tn a into Tn by b plus Fn. It's a divide and conquer recurrence relation, my dear friends. So if you see option A, Fn is big theta of n power log a to the base b minus epsilon. See, that is the first case of master theorem. Whenever the first case of master theorem is satisfied, the time complexity is given by theta n power log a to the base b. And that is exactly what is given here. That is exactly what is given here. So this is correct. The second option, he not mentioned anything about n power log a to the base b. He not mentioned anything about n power log a to the base b. Okay, without knowing, just knowing the type of Fn, you can't decide anything, sir. So this fails because we do not know about n power log a to the base b. Even this fellow D option also fails. B and D options fails because nothing is mentioned about n power log a to the base b. Without knowing, because the master theorem is based on the comparison between n power log a to the base b and Fn. If you do not know about n power log a to the base b, just knowing the type of Fn, you can't decide anything. So these two we cannot make any comment on that based on the master theorems. Okay, any other result also does not work because unless or until you know AB, you can't make any decision here, sir. And if you see C option, he says that Fn is of same order of growth as n power log a to the base b, then Tn is, of course, here we should also have the regularity condition, sir. If Fn is of the same order of n power log a to the base a and regularity condition is satisfied, then the answer is n power log a to the base b into log n. Okay, but log n is missing. Of course, sorry, no need of regularity condition. I'm sorry, it's not, it's the second, Second case, no, sorry. Second case, we don't need regularity condition. Second case, we don't need regularity condition. It should be n power log a to the base b. Log n, you can say, sorry, n power log a to the base b is mentioned. So Tn is theta n power log a to the base b log n. But where is log n? Log n is missing. That's why it is wrong. So that's why C is wrong, my friends. C is wrong, my friends. Sorry for that. Third result, third condition, we require regularity condition. For this, we need the regularity condition, my friends. It's a direct application. And one more question. See, for this, I'll give you a shortcut. You can remember this. Whenever such type of problem comes, you please use this shortcut. You use this shortcut, you can get the answer within no time, my dear friends. See, this is the shortcut. Suppose you are having Tn is equal to Tn by B1 plus Tn by B2 plus and so on Tn by Bm. There is N1 multiplied with some coefficient, N2 multiplied with some coefficient, fraction actually. It is of a form some fraction less than 1. If sum of sizes of subproblems, here you have 1 by B1 plus 1 by B2, whatever the subproblem fractions are there, no? If sum of these sizes is less than 1, then the complexity is theta n. If sum of these sizes is equal to 1, then the complexity would be theta n log n. So in this particular problem, if you see the subproblem sizes half and 2 by 5. Half plus 2 by 5 is how much, sir? 10 is the LCM. It is 5 plus 4, 9 by 10, which is less than 1. So if this value is less than 1, what is the answer for this problem, my dear friends? What is the answer for this problem, my dear friends? Of course, this can be solved using recursion tree method, but it's a very standard one. You can remember this as a result, my dear friends. Of course, the idea that the particular result which I given is also based on the recursion tree idea only. Okay, of course, recursion tree directly they don't use, sir. After recursion tree, you have to do the verification, substitution method you have to do. Very good, Navin Nayak. B is the answer for this. Directly you can write the answer for this, my dear friends. Please remember this type of problems are very, very common, sir. There is one more one like, Tn is equal to T of alpha n, T of 1 minus alpha n plus beta n. See, this is beta n, this some constant times of n, sir. Okay, same story here, alpha plus 1 minus alpha is 1. So what is the time complexity? Time complexity is theta n log n, my dear friends. Time complexity for this is theta n log n, my dear friends. Hope you understand. All of you able to follow? One more problem. Tn is equal to T of n power 1 by a plus 1 with T of b is equal to 1. Then what is Tn, my dear friends? Shall we do in a very short manner? Shortcut. So here, what you do is, you take n is equal to some b power m. You take n is equal to some b power m. So with that, what happens? This T b power m is equal to T b power m by a plus 1. Right? Now, you can consider this T of b power m as some function of m. So, with that, what happens? This would reduce to Sm is equal to Sm by a plus 1. Okay, very good, sir. Let us see, Satya, programming wala, let us see that. Whether it is D or B, let us see. Yeah. So, now, Sm by a, now the constant manipulation need to be done. Here it is Tb. Tb is nothing but T of b power 1. Because T of b power m is Sm, it is S1, my dear friends. But Tb is 1, so S1 is 1. So you also got the condition S1 is 1, my dear friends. You got S1 is equal to 1. So we can apply master theorem. By master theorem, What is the comparison you are going to make, my dear friends? M power log 1 to the base A versus Fm, here it is 1. This is m power 0, which is 1, and this is also 1. Both are of equal order of growth. Both are of equal order of growth. Therefore, Sm is equal to now what we need to take? See, actually it is theta. Sm is equal to theta log m. Theta log m, you have to take it. Definitely complex. You are computer science student, Subhaskar, or complex analysis you want me to do? Complex analysis you want me to do in the marathon series? Would like to, but problem is with mathematics I have to do discrete mathematics. So once that particular portion is completed, I'll be doing discrete mathematics when complex is happening. So yeah, Subhaskar. So at that particular time, I'll be doing complex analysis. I'll be doing discrete mathematics. So that may be little difficult, but we'll try to do sometimes if possible. Can't promise. See, right now things are very hectic here. Okay, because paid classes to be completed here also I need to discuss. So definitely I'll come up with that, sir. Definitely I'll try to do that. Complex I'll definitely try to do it. Or you can just connect with me. I give you, you can connect with me. I'll give you some ideas where you can, get these methods or material at least, so that you can go through that. Okay. Subhaskar, I can help you out. You can connect with me in the Telegram group. You are a regular student. Yeah. You are a regular student. Yeah. A YouTube student. Subhaskar. Nice. So now it is theta m, but what is m, sir? Here you already seen n is equal to beta b power m, means m is equal to log n to the base b. Log n to the base b. So it is log n to the base b. So this has to be a, because the base here, my dear friends. No problem. Still, see, it doesn't matter, sir. I'm just asking. See, based on that, see in what way I can help you. That's what I'm doing. Don't worry. You can connect with me in my, you can separately ping me. I'll tell you how to go with that complex analysis in a very simple manner. Okay. I'll help you. Don't worry. So the correct answer for this is option B, not option D. Sure, sir. Okay. See, actually, after this step, if you don't want the master, because master theorem, some people get confusion how it is base A. So if you want to understand, then you have to go for the detailed method, my dear friend. Then if you go for the detailed method, like iterative method, if you go for iterative method, then you will understand that properly. Sm will be equal to Sm by A plus 1. Then Sm by A will be equal to Sm by A square plus 1 plus 1. So from this you can understand the pattern. You can easily see that Sm is equal to Sm by A power some k, let us assume. Okay. Plus, see, because when it is, when you see this here, it is Sm by A square, then it is plus 2. So when it is Sm by A power k, then it is k, my dear friends. So you have to continue till m by A power k is 1, means m is equal to A power k. That means what, sir? K is equal to log m to the base A. That is the value, because here S1 is 1. Obviously, Sm will be equal to 1 plus k. So obviously, Sm is of order theta k. Sm is of order theta k, where k is equal to, what is k? Log m to the base A. But what is log m to the base k? What is m, my dear friends? M, again we see here, m is nothing but log n to the base b. So here it is log a and log n to the base b. So what is the correct answer for this? Log to the base A, log to the base B, n. So like that we can get the answer for this, my dear friends. I've seen a lot of people done this particular problem in a very strange manners, my dear friends. This is a simple way you can handle this problem. It's a simple problem. Don't mess up with such problems. Unnecessarily starting from here, people use the iterative method. You'll be in danger, my dear friends. You'll be in very big danger. That also can be done. Tn will be what, sir? Next time they substitute n means 1 by a. Okay. In place of n power 1 by a, they substitute n power 1 by a whole power 1 by a. That is n power 1 by a square plus 1 plus 1. Like that they go on reducing it to a very strange manner. Okay, you can do that. That is also same only. Directly you get that particular form. But this is the easiest way of handling, my dear friends. This is the easiest way of handling this particular problem. Got it? Okay, next problem. Please try this, sir. Please give the answer. See, we all know that an array of 25 distinct elements is to be sorted using quicksort. Assume that the pivot element is chosen uniformly at random. So out of 25 elements, one element is selected at random. The probability that the pivot element gets placed in the worst possible location in the first round of partitioning. See, what is the worst position for quicksort algorithm, sir? What is the worst position for pivot element for quicksort algorithm? What is the worst position for element in quicksort algorithm, my dear friends? Please tell me. Please tell me. Am I not getting your notifications? First and last. Very good, Pranav. First and last. So what is the probability that we get worst position? Wrong position. That is probability that the pivot is in first or last position. So first or last position means 2 positions out of 25. That is 0.08 or whatever it is. Write down that. 0.08 you can write. Now the next problem. There are n unsorted arrays a1, a2 and so on an. Assume that n is odd. Assume that n is odd. Each of a1, a2 and so on an contain n distinct elements. They are all unsorted. There are no common elements between any two arrays. That is, all the elements are distinct. Thank God. The worst case time complexity of computing the medians of a1, a2 and so on an, my dear friends. See, here he is giving you hint that find median of each array using median of median algorithm. Using medians of medians algorithm. And for each array, this can be found in theta n time. For each array, this can be found in theta n time, my dear friends. For each array, this can be found in theta n time. Now, for these n arrays, the median of medians can be found in, okay, because for each array it is n means, and for this all the arrays we have to find medians of median, okay, because there are n elements, n medians you are going to get. Again, that for n elements you can find median of medians in theta n time. See, there is an algorithm, sir, median of medians. So what they do in this particular algorithm is, I'll just tell you, not complete story, I'll just give you the hint or outline of that particular algorithm. The idea is this: we have suppose an array of size n. They divide into pieces of size n by 5, n by 5, n by 5, like that. So for each those pieces, because 5 elements are there, in constant time you can sort them and you can find median of that particular fellow. Again, next n by fifth array is there, no? That n by fifth array, we find the median. That is sort and find the median. Sort and find the median. That is, you are going to get n by 5 medians, my dear friends. Am I clear? Hope you understand. So, we are going to get a new array of n by 5 elements. You are going to get a new array of n by 5 elements. Recursively solve this to get a median. Then, that particular median, using quicksort algorithm, try to place in its correct position. Then using recursively find that particular median in its correct position using quicksort algorithm. So this particular algorithm is having complexity theta n, sir, though we call it as median of medians algorithm. So the complexity of that particular algorithm is order n. Am I clear? So that is the logic here, my friends. Because that particular algorithm need to be done for how many? N such fellows. So for one fellow it is theta n, means for n fellows it is theta n plus theta n plus theta n. How much, sir? Theta n square. Now again for these arrays, okay, you can find medians. Am I clear? That median of these n arrays can be found in, these n elements can be found in theta n times. So the complexity for this would be, of course, theta n square or order n square you can mention. Very good, Pranab Paul. Order n square, my friends. It can be done in order n square, my friends. So there's that particular algorithm, famous algorithm known as median of medians algorithm. They use that particular algorithm to find median in order n time, my friends. If time permits, sometimes we try to discuss that algorithm because the analysis is very involved in this. So that may take little more time for understanding. Otherwise, the remaining part is very simple for this problem. Now there is one more problem here. These are all direct questions, sir. Let P be an array containing n integers. Let T be the lowest upper bound on the number of comparisons of the array elements required to find the minimum and maximum values in an arbitrary array of n elements. Which of the following choices is correct? See, actually for finding minimum and maximum, we have two algorithms. One is the straight min-max algorithm. The other one is recursive min-max algorithm. See, for straight min-max algorithm, the best case is n minus 1 comparisons required. Best case we require n minus 1 comparisons. Worst case you require 2n minus 1, that is 2n minus 2 comparisons, my dear friends. Whereas for recursive min-max, my dear friends, it is 3n by 2 comparisons required. 3n by 2, that is 1.5 n minus 2 comparisons. So order, if you take it, 3n by 2, order 3n by 2 comparisons required. So if you see, out of these two, this is the lower bound and this is the best upper bound, my dear friends. This 2n minus 1 is more than that, so that can be ignored. So we are going to consider this particular option here because it has to be best case is n, worst case is 3n by 2, my dear friends. So we are going to take the option C in this particular case. See, that particular number of comparisons. See, if you are taking only order bound, when you are taking a bound, you can ignore the constant, my dear friends. See, here also bounds are ignored. The constants are ignored here also. Here also it's not exact comparison, sir. It is just the bound. That's why that minus 2 is ignored. Always it is 3n by 2 minus 2 only, sir. Always it is 3n by 2 minus 2 only. The number of comparisons exactly you want, 3 by 2 minus 2 only. Yeah, correct one. And it is a straight question, sir, straightforward question. Please try to answer this. A common sense question, informative question, nothing more than that. Try to answer this. Okay, let us check that. Anyhow, we are worried about bonds. Let us see that. Very good. See, Babu, Srinu Khetawat, that is wrong, sir. Please check that. That is wrong option. See, my dear friends, Merge sort always perform theta n log n comparisons. Insertion sort, best case is theta n and worst case is theta n square. Best case for insertion sort happens when it is a sorted array or reverse sorted array. Am I clear? So best case is possible for the sorted arrays. Insertion sort works better. Insertion sort works better for a sorted array because it is a sorted array. It works in theta n time for insertion sort, my dear friends. No problem, Ketawat, no problem. Selection sort always theta n square. Whether it is sorted or whatever it is theta n square. Okay. Whereas quick sort, actually quick sort works in worst case for sorted arrays. For sorted or reverse sorted arrays, quick sort works in the worst case. So for this, it would be theta n square for sorted arrays. Last element as the pivot. So when you take this as the pivot, obviously, what happens? 97 will be there. One side it is Tn minus 1, one side it is T1. So the complexity will be theta n square, my dear friend. See, some people have this particular problem with swaps for insertion sort. So if you consider the movements also as swaps, okay. So what happens? The swaps will not be there for insertion sort. So insertion sort will do it in theta 1 time. Am I clear? So insertion sort will be done in theta 1 time, my dear friends. Am I clear? See, for quick sort, because of recursion stack space will be there, sir. Recursion stack space will be recursive log and recursion stack space will be used. Otherwise, it doesn't need any extra space. It is an in-place algorithm. Quick sort is an in-place algorithm, my dear friends. Okay. Selection sort will have minimum number of swaps. Maybe they are not considering insertion sorts. That's what I mentioned. They may not be considering the swaps in insertion sort. In that case, then we have to go for that. See, there may be some questions which are subjected to the conditions. Okay, because if it is given in a test series or in some in which PYQ it is given, PYQ, then we have to see. You please send that particular question once. I'll just check it out and let you know that. Okay. See, that's what I'm saying. That if the shifts are not considered as swap, then what happens? Okay. See, in selection sort also what happens, sir? The minimum element is placed in its correct position. So minimum element. See, in selection sort, it's not bubble sort, selection sort. Forgot. Let us see that. You please send that particular question. We'll discuss that. Okay, I'll see that. Next one. What is the worst case number of arithmetic operations performed by recursive binary search on sorted array of size n, my dear friends? What is the worst case number of arithmetic operations performed by recursive binary search on a sorted array of size n, my dear friends? So we are not doing any swaps there. No, we are not doing any swaps there. The same is the case with insertion sort also. Nothing is moved. Yeah. See, my dear friends, whether it is a sorted array or unsorted array, binary search. Can you perform binary search on unsorted array? Can you perform binary search on unsorted array? That's what, sir. So sorted array obviously Tn by 2 plus 1 because either left part or right part and finding the mid element. So obviously this is it. And what is time complexity of this? This is theta log n, my dear friends. This is theta log n, my dear friends. This is theta log n, my dear friends. So D is the correct option. So if it is so, then we should consider, like, you know, the swaps of insertions, the insertion sort, they should not be considered as swaps. Okay, so selection selection, I mean, in selection sort, it is a proper swap. So like that we can go for it. See, when it is a old gate question now, because they're not given the answers before 2007, the questions, because yeah, it's a bit confusion, sir. But as I mentioned, for that, if it is a after 2007 question, they are releasing the solutions and you can challenge the questions. Now, before that, whatever solutions are given, people are going with it. Am I clear? So even for that, there is no strict rule kind of things. Yeah. Next one. Please try this problem, sir. Consider the following undirected graph. Consider the following undirected graph. Choose the value of x that will maximize the number of minimum weight spanning trees, MWSTs of G. The number of MWSTs of G for this value of x is what? So, for what value of x? There are two questions in this. For what value of x it will have more number of minimal spanning trees? More possible minimal spanning trees are there, and how many are there? Both you have to answer. Of course, because it is numerical answer type, one answer you have to give. That is, with that value of x, how many minimal spanning trees are possible, you have to tell. See, my dear friends, let us try the value, because for minimal spanning tree problem, if suppose all weights are distinct, you get unique minimal spanning tree. If they are distinct, you are going to get unique minimal spanning tree. So, if you want to get more minimal spanning trees, the idea is you should have equal keys. You should have equal keys, my dear friends. Then, suppose the keys are involved in any particular cycle, you can use any one key in that particular cycle, my dear friends. That is, the choicing can be done. That is the idea, my dear friends. That is the idea here. So, let us try different values for x. Let us try x is equal to 1. What happens? If x is 1, what happens? Let us see. And let us use the simple Kruskal's algorithm here, sir. Let us use simple Kruskal's algorithm. First 1 is selected. Obviously, if x is 1. Then after that, next smallest is this one. Next, this one is done. These three are obviously selected. See, when x is 1, yeah 3. X is 1, yeah 3. These three edges are obviously selected. Now, after that, this 4 cannot be selected. From these two 4s, any one 4 can be selected. So, selecting either this 4 or you can select this 4. Any one of them can be selected, my dear friends. That is, there are two minimal spanning trees possible. So, the number of minimal spanning trees possible in this case is the number of minimal weight spanning trees possible when x is equal to 1. See, when the value of x is 1, number of minimal weight spanning trees would be 2, my dear friends. Yes, Pranav Paul, that's it. See, either you have to use a number within this particular range, or you have to use the number which is outside the range. Outside the range is useless, because if this number is outside the range, with 4 and 5 I can complete minimal spanning tree. So using x value more than any of these numbers is a bad idea. Using any x value anything greater than the values which are present here. Suppose you take it as greater than 6 or greater than 6. In that particular case, 1, 3, 5 and one of these 4 will be selected. 2 minimal weight spanning trees are possible. So that is same as this one only. So that is not a better idea. So for x is 1, suppose if you take x is 2 also, same story. If you take x is 3 also, same story. If you take x is 4, also, this 4 and this 4. In that definitely this 4 can be selected. Anything you can do, sir. It's nothing like that. So with maximum, are you going to get more, or minimum, or you are going to get more? Yeah. It is. See, it is a subjective thing, sir. Because if you construct a different tree, things may be different. Am I clear? Like that. So here also it is 2. With 4 also it is 2. Now with 5, when you take this as 5, in this particular case, the story is interesting. When you take it as 5, the story is interesting. So this can be selected. This can be selected. Now this 4 is always ruled out. One of these 4 can be selected. That is 2 choices you are having. Once you select, one of these 2 can be selected. See that particular cycle, if you are having 2 choices, this particular cycle, if you see this particular cycle, what are the possible cycles which you can make, sir? See, the main idea here is, what are the possible cycles which you can make? The one cycle which you can create here is this cycle. So it has to be either 3 or 5. But both will be selected. Both will be selected. 3, 3, both will be selected. Then this 5, because this 5 is ruled out. But when you make it 5, either this or this will be selected. So that is the better idea than selecting any value other than that. So in this cycle, if you are having equal values, so out of these 2 fellows, any one can be selected. So that is the better choice. Selecting 3, obviously what happens, this 3 will be selected. So other numbers will be selected. This 5 can be completely ignored because there are other smaller value outside this. So selecting 5 is a better choice here, my dear friends. That is the idea. So for this problem, when it is 5, you are getting 4. Because for these 2, there are 2 choices. For these 2, there are 2 choices. 2 into 2, 4 choices will be there. So 4 is the answer for this. One more similar question was asked in GATE. Consider the similar type of question they are regularly asking, sir. Similar type of questions they are regularly asking, my dear friends. Consider the following undirected graph with edge weights as shown in the figure. The minimum weight spanning trees of the graph. The number of minimum weight spanning trees. How many minimum weight spanning trees are possible? See, my dear friends, first try to select all the smallest edges, and you can continue as long as there are no cycles. And the smallest edge weights all can be selected and without forming cycle. So they all can be selected, my dear friends. They all can be selected. Now here this 0.9 and this 0.9, these 2 edges are ruled out. They cannot be selected because they are forming cycles. Now out of these 3, because here we have 2 components. One is above and one is below, 2 components. If you can connect them, because how many edges you selected so far? How many edges you selected so far? 1, 2, 3, 4, 5, 6, 7 edges you selected. Total 9 vertices are there. So we require one more edge. So for that edge, you can select either this or this or this. So what is the answer for this? 3 is the answer. Babu, now, it is not 7, it is 3, sir. It is just 3 is the answer, not 7. 3 is the answer for this. Yeah. Pranab Paul, 3 is the correct answer. So one more simple question, sir. Please answer this question. Vanshika, good. Simple question it is. It looks dangerous, but it's a very simple question, my dear friends. It's actually a very, very simple question. See, actually we are having a graph with vertex set 1 to 100 and edge set is given by Vij, where I varies from, that is Ij values are varying from 1 to 100, sir. That is I can be 1, J can also be, I can vary from 1 to 100, J also can vary from 1 to 100. See, always I is less than J, my dear friends. I value is less than J. And the weight of edge is given here. Vi to Vj, the edge weight is given here. Now, if you actually observe here, suppose if I take V1, V2, they are connected. They are connected. As long as I is less than j, they are connected, sir. There is an edge between them, and the weight of the edge is difference of the values, difference of the indexes. So here it is v1, v2. So the length of this edge is mod 1 minus 2, which is nothing but 1. So length of this edge is 1. Now v1 to v100, is there any edge? Yes, there is a edge from v1 to v100. And you know what is the cost of the edge, or what is the weight of the edge? 1 minus 100, that is mod 9 minus 99, which is 99. So the edge cost is 99. But you want minimal weight spanning tree. When you can get the minimal weight spanning tree, my dear friends? Spanning tree means, because here all the vertices are adjacent to all other vertices. Every vertex is adjacent to every other vertex, sir. Here you are going to get the complete graph. Here you are going to get the complete graph. Okay. But you don't have to consider, because you require the minimal weight edges only. We require only minimal weight edges. So if you are having V1 to V2 will be having least weight. V2 to V3 will be having least weight. V3 to V4 will be having least weight. Continuing this way, V99 to V100 will be having least weight, that is 1. These are the least weight edges. There may be other edges from V1 to V3, V1 to V4, V1 to V100, but they all will have highest cost. But when you are creating the spanning tree, you start with the minimal weight fellows. So you select this fellow, you select this fellow, you select this fellow, and you select this fellow. So 100 vertices are there, means you select 99 edges, each of cost 1. So what is the weight of minimal weight spanning tree? 99 is the answer. So the answer for this problem is 99. So that logical idea, it's a general puzzle only, sir. You can do it in discrete mathematics, you can do it in algorithms, you can do anywhere. Even in aptitude also this question can be asked. Even this question can be asked as an aptitude question also. Okay. So yesterday I missed some questions, so I just adding that here. It's a last year question, interesting one. So let us take 1, 2 and we stop it. Okay. And there may be some more problems. We'll try to do it with data structures. Data structures I am coming up on Monday, second new year. We start with new subject, BYQs. Later on we can also do this marathon series. Yeah. So this is a very interesting question. Actually last year only he asked. Let G is equal to V be a directed graph. Directed graph it is. V is equal to 1, 2, 3, 4, 5 is the set of vertices and E is set of directed edges as defined by Aij is equal to 1 for I less than or equal to j less than or equal to I less than or equal to 5. And Aij is equal to 1 indicates a directed edge from node I to node j. See, actually if you observe, as long as j less than or equal to I, then only we are having 1, otherwise it is 0. So can you tell me what is this adjacency matrix, my dear friends? Can you tell me what is this adjacency matrix, my dear friends? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. First, let us write down the adjacency matrix. Let us write down the graph. Then you can say the answer for this question, my dear friends. Here what he mentioned, sorry, what he mentioned in this problem, j less than or equal to I. J less than or equal to I. See, 1 less than or equal to 1, it is fine. 2 less than or equal to 1. Is 2 less than or equal to 1 fine, sir? It's not 2 less than or equal to 1. It is 2, 1 means 1 less than or equal to 2. J is the second index, not the first index. Okay. J is the second index. Second index less than or equal to first index. So when you have 2, 1, okay, when you have 2, 1, see, when j less than or equal to I, this means I greater than or equal to j also. No. When j less than or equal to I, you can consider I greater than or equal to j. That is easy for you. So 2, 1, fine. 2 greater than or equal to 1, fine. 2 greater than or equal to 2, yes. But 2 greater than or equal to 3, no, no, no. 1 greater than or equal to 2, no. 1 greater than or equal to 3, no, no, no. Very good. It happens. Next one. 3 greater than or equal to 1. Yes. 3 greater than or equal to 2. Yes. 3 greater than or equal to 3. Yes. Sorry. Yes. Sorry. Yes. And that is the story. That is the story. So this is your adjacency matrix. Once you know the adjacency matrix, you can create the graph, my dear friends. Let me write down the vertices. Anywhere you can write down 1, 2, 3, 4, and 5. Now here 1 to 1 is there. I am ignoring self loops. I am ignoring self loops because I am not very much interested in them. Okay. So I am ignoring self loops for simplicity. Next, what is that? 2. 2 is adjacent to 1. That is 2 to 1 direct edge is there. No, sir. J less than or equal to I is there. J less than or equal to I is there. Pranab Paul. I don't know. See, I am solving this. Suppose if we give that, that also can be solved, sir. That also can be solved. Okay. But let us see this first. So 2 to 1, 2 to 2, ignore it. 3 to 2 is there. 3 to 1 is there. 4 to 3 is there. 4 to 2 edge is there. 4 to 1 edge is there. Now 5 to 4, 5 to 3, 5 to 2, and 5. So this is your adjacency matrix, sir. This is your adjacency, this is your directed graph, digraph. Adjacency matrix, and further this is the digraph. Now let us see the question. A directed spanning tree of G rooted at R is defined as a subgraph of T of G such that the undirected version of T is tree and T contains a directed path from R to every other vertex in V. See, self loops, I already told you, because I am interested in trees. When you are finding trees, why those self loops? It will confuse you more. I just removed them because I already read the question now, so I just removed them. They are not useful, that's why I removed. If you want, you can just write down self loops, sir. Put small self loops so that no one will trouble. Put small self loops like this. Am I clear? You can put them, no problem. See here, I just read it. Fine, let me read it once again for you. Let me read it once again for you. See, my dear friends, what he's saying, he is defining as directed spanning tree of G. Directed spanning tree of a tree, directed spanning tree is defined like this. How it is defined, sir? It is having a root and it is a subgraph. Subgraph means what, sir? It is a part of the graph. It is a part of the graph. Means it contains same vertices and same edges as G. First of all, it is a subgraph. Now, if you remove the directions, see, I'll just show you. You see here. I'll just show you one simple example. You see here. Now look at this small example I'm showing. You please tell me whether it is a subgraph or not. Whether it is a subgraph of G or this graph is there, no? For this graph, it is a subgraph or not? For the given graph, it is a subgraph or not? For the given graph, it is a subgraph or not? Pranab Paul. So first thing is, it is a subgraph. Now, it is a rooted a tree. Suppose, let us take root as some fellow. Suppose root as some fellow 5, you take it. Now, what is it? It is saying, T contains a directed path from R to every other vertex. Now here I take root as 5, sir. It is a directed tree which is having 5 as root. From 5 to every other vertex there is a directed path. From 5 to every other vertex there is a directed path. Is there or not? Of course, he not mentioned spanning subgraph, but I am taking it, sir. Yes or no? Yes or no? Yeah. Because it is a spanning tree means what happens? It should contain all the vertices. If it is a just, he mentioned spanning tree, na? Sorry, spanning tree he mentioned, therefore it should contain all the vertices. Spanning tree he mentioned means it should contain all the vertices. Yeah. So it contains a directed path from R to every other vertex. Now, if you see this particular graph, if you remove the directions, is it a tree? If you remove the directions, is it a tree? If you remove the directions, is it a tree or not? It is a tree. Correct or not? So what is saying, a directed spanning tree of G rooted at, in our example 5, is defined as a subgraph of G such that undirected version of that is tree. So undirected version of this is a tree, and it contains directed path from R to every other vertex. So from 5 to every other vertex it contains a directed path or not? Now I'll show you some more examples of similar such trees. 5, okay, 4, 3, 2, 1. It should be the subgraph of original graph. Now look at this, sir. Now look at this. Even this fellow is a spanning tree according to the given definition or not? Even this is a spanning tree according to given definition or not? Is it a now the question is number of such directed spanning trees rooted at vertex 5 are possible. Number of such spanning trees rooted at vertex 5 are possible. See, actually if you observe, there is no edge going from other vertices to 5. So obviously 5 has to be root. Obviously 5 has to be root. No other vertex can be root, sir. If you don't take 5 as the root, you cannot get spanning tree. You can get trees. See, rooted at 4, you can have a tree which can have other vertices like 3, 2, 1. But if you want to contain all the vertices, definitely it has to be rooted at 5 only, my dear friends. Now you understand the logic. Now let us answer this particular question, my dear friends. Which one is pendant vertex, my dear friend Pranav? Which one is pendant vertex? See, here it is a directed graph, na pendant vertex. How you define it? You are talking about undirected graphs. For directed graph, we have in degrees and out degrees. It's not 5, sir. It's more than that. Let us see the story here. So let me give you a simple story for this. First of all, let me give you a simple story. Shall I erase this so that we can build the complete story slowly? Suppose, let us go with a, now let us go with a simple story. Suppose you have a single vertex, suppose in this story we have a single vertex. How many such spanning trees are possible? Only one vertex is there. See, here it is 5 by 5 is given, na? Instead of attacking the 5 by 5, let us start with 1 by 1, 2 by 2, like that we attack. We understand the logic, then we generalize it for 5 by 5. Okay, so let us try that way. So single vertex is there. How many spanning trees are possible? Number of spanning trees possible is only one. Yeah. Now suppose if it is at 2 vertices are there, 2 and 1. Number of spanning trees are possible here is, see, 2 has to be root. From 2 to other vertex, you have to create the directed edges, directed path. So only one path is there. Here also number of spanning trees is equal to 1. Now see the story here when you are having 3 vertices. 3, 2, 1. When you are having 3 vertices, let us see the story, my dear friends. Now look here. Now look here. See, from 3 you have to create the directed edges. Actually, if you observe in the graph, 3 to 2, 3 to 1 also edges are possible, and 2 to 1 edge is possible. So from any higher number to the lower number, edges are possible. From any higher number to lower number, direct edges are possible. So if you actually fix 3 here, the other numbers are 2, 1. So how many permutations are there for 2, 1? How many permutations are there for 2, 1? 2, 1 can be written as 2, 1, yeah, 1, 2. 2, 1, yeah, 1, 2 are permutations of 2, 1. Okay, so with 3, from 3, if you are going to the lower number, direct edge will be there. And from that number, if you are going to the lower number, edge will be there. But from any number, if you are going to the lower number, edge can be created. But from any number, if you are going to the higher number, edge cannot be created. So that edge stops there. So for the next number, you can create a direct edge from root, my dear friends. You understand the logic? Here we are going to create a direct edge. See, I'll just explain this, you'll understand that. See here, these are the 2 permutations possible for 2, 1. For 2, 1, these are the 2 permutations possible. So from 3, what you do is, you try to create the edges like this. From 3 to 2, can you go? From 3 to 2, can you go? Yes, directly go to 2. Directly go to 2. Then in this permutation from 2 to 1 you can go. Yes, then directly go to 1 like this. Then directly go to 1. So here I created one particular directed path. Now look here. Second one I am trying to tell you. From 3, can you go to 1? From 3, can you go to 1? Yes, create a directed path. But from 1, can you go to 2? No. See, in the given permutation, how we need to create the different spanning trees, I am explaining. In the given permutation, how to create the different spanning trees, I am explaining. So 3 to 1 you can go in this permutation. We start with 3. First you can go to 1, so directly go to 1. But from 1 to 2 you can go. 1 to 2 you cannot go. So you stop this here. Then directly from 3 to 2 you go. Then directly from 3 to 2 you go. Directly from 3 to 2 you go. So these are the 2 spanning trees I can create it. Now if you understand this logic, the next one can be easy, because whenever there is a inversion, you stop it. That is the logic which he used here in this particular problem. Now the story is very interesting. Okay, here how many spanning trees are possible? For this number of spanning trees, 2 spanning trees are possible. Now see the story, my dear friends. When you start with 4, the other vertices are 1, 2, 3. Now tell me how many permutations of 1 to 3 are there? How many permutations of 1 to 3 are there? How many permutations of 1 to 3 are there? 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 2, 3, 1, 2, 3, 2, 1. Now what I do, for every permutation I create a spanning tree using the same logic. So I will not be changing the color, sir, because it is a bit confusing. 6, I will show you 6 spanning trees. If you understand, you can answer the question for the given problem. If you understand the logic, you can answer the given problem by difference. Now for 4, from 4 you can go to 1, but from 1 to 2 can you go? 1 to 2 you cannot go, you stop here. Then from 4 you can go to 2. From 2 to 3 can you go? No, stop there. Then 4 to 3 you go. This is one spanning tree. Now for this, from 4 you are going to 1. From 1 to 3 can you go? No, stop there. Then from 4 can you go to 3? Yes, 4 to 3 you go. From 3 to 2 you can go? Yes. This is spanning tree corresponding to this permutation. Means for every permutation of remaining numbers, I can create a spanning tree. For every permutation of remaining numbers, I can create a spanning tree. Now here, let us see this particular one. 4 to 2 you can go, and 2 to 1 you can go, but from 1 to 3 you cannot go, don't worry. 4 to 3 you can directly go. 4 to 3 you can go. See, these are all directed edges, sir. These are all directed edges. Hope you understand. Similarly, for this fellow, 4, 2, I'm sorry, I made a mistake. 2, 3, 1, I think, right? 2, 3, 1. Please be careful. So 4 to 2, 2 to 3, no. Up you cannot go, down you can go. So leave it. Then 4, this stopped here. Then 4 to 3 you can go, 3 to 1 you can go. Similarly, continue. This one, here I am writing it, sir. 4, 4 to 3 you can go, 3 to 1 you can go. Then 1, after 1 you cannot go to 2, stop there. Directly from 4 to 2, you start the next one. You start the next one. Now create the spanning tree for this. From 4, you create to 3. From 3, you can go to 2. From 2, you can go to 1. 4, 3, 2, 1. So these are the 6 spanning trees possible, my dear friends. Wonderful, wonderful, Pranab Paul. That is the idea. So the number of spanning trees possible for this is 24, like that. Suppose if I give you 100 by 100, in that particular case, what will be the answer? 99 factorial. This can be generalized. Now, because you done so much work now, I'll give you number 7. I am just taking another level. I am giving number 7 and I give a permutation of 1, 2, 3, 4, 5, 6. You try to construct a spanning tree. You can give that particular solution in the Telegram group, my dear friends. You can give that particular solution, draw that particular spanning tree and put it in your, write that particular solution, send that particular solution in our Telegram group. See, it's not possible, but for those with clicks, now you understand this logic. Next time when you get this question or similar type of question, see, algorithm is all about that. We learn some design technique. It does not mean that the same design we have to use in the problem, sir. You get a new problem. Suppose if this design can be applied to that, you can solve that. For example, dynamic programming approach can be used for rod cutting problem, Fibonacci number problem. You can apply matrix chain multiplication. You can apply for longest common subsequence. They are not same problems, no. They are not same problems. The idea, once you understand, future it would be better, sir. You get different logics. You get different ways of thinking about the questions. That's what, sir. See, similar type of questions only they'll ask you. See, you see this particular question. They asked this question in 2018. Again in 2021, this question was asked. Again in 2021, this question was asked. See, in C programming, you might be using only recursion. Are you using dynamic programming? Using recursion and using dynamic programming are two different things. Okay, don't get confused with it. Yeah, 7 is there. So I'll give you a permutation of 1, 2, 3, 4, 5, 6. So I'll give, because 6 factorial permutations are there. Yeah. So for example, 3, 2, 1, 5, 6, 4. Can you give a spanning tree for this? Can you give a spanning tree for this according to our rules? So from 7, you can go to 3. From 3, you can go to 2. From 2, you can go to 1. But after 1, going 5 is wrong. Stop there. Then what you do? From 7, you can go to 5. From 5, you cannot go to the next higher number. Stop there. Here also it is stopped. Then from 7, you can go to 6. From 6, you can go to 4. So this is the spanning tree which is created, my friends. Hope you understand. Very good. Okay, we'll conclude quickly, sir, with some more general questions. We taken a long session. It's almost 2.5 hour sessions I taken. PDF password. Let us create a password for the PDF. The password for this PDF is, so this is a password protected PDF. Okay. So the password for this is ALGO, algo. Then answer for this problem. Or no, don't use answer for this problem. Answer for 6 vertices problem. Okay? Okay, answer of this question you want? Okay, answer of this question. Answer of this question or answer of 6 vertices problem. Answer of this problem or answer of 6. See, for 5 vertices, answer is 4 factorial. For 6 vertices, what is the answer? So you please tell me 5 vertices answer, yeah, 6 vertices answer. You please tell me 6 vertices. So that is the answer. ALGO followed by ALGO, not Babu. 5 factorial is how much? What is 5 factorial, Babu? Pranab Paul. 5 factorial is 125 nowadays, huh? Is they changed it or what? That is the password. But I am clearing it. Please remember this. So this is password, and also giving password. Yesterday's one also I not given to you. That is DM42. DM42 is the password for discrete mathematics. Both I will send it today itself. Immediately after the class. Now, see, G has a unique minimal spanning tree if no two edges of G have same weight. Without watching my class, why should I give PDFs to students, sir? I am a content developer for them. Okay, I am not a content developer for the students. I am a teacher. So you want my content, then you have to hear my class. Right? See, one more thing is, people don't have seriousness, my dear friends. The PDF password idea is, people don't have seriousness. They just collect the papers. See, even if I don't keep the password, nothing will happen, sir. They just keep on collecting them. They collect the material. They collect the solution manual for all nonsense things. But what is the use? Okay, I always tell them. It's not about mehnat and all, sir. It's not mehnat. People, those who want, they have to work hard now. Am I clear? If they want something, they have to work hard for that, or at least attend the class. Right? Every PDF will be password protected, sir. Please remember. Now, in G be any connected weighted undirected graph, G has unique minimal spanning tree if no two edges have same weight. See, if all the weights are distinct, minimal spanning tree is unique. This is true. G has minimum spanning tree. For every cut of G, there is a unique minimal weight edge crossing the cut. See, this is actually Prim's algorithm. In Prim's algorithm, what happens? We are going to create a cut, and the edge crossing that, the edge with minimal weight crossing the cut will be selected. So generally what happens, once you create a cut, if two edges with minimal weight are there, then you select any edge arbitrarily. But if every edge or the minimal weight edge crossing the cut is unique, then obviously you get the unique minimal spanning tree, my dear friends. So this is also true. Both are true. Both the statements are true. This is actually a statement related to Prim's algorithm. It is a statement related to Prim's algorithm, my dear friends. Okay. Next one, there exists a minimal weight edge in G which is present in every minimal spanning tree. This one you want? Okay, I'll just tell you. See, first one is, if all edges are having distinct weight, minimal spanning tree is unique. Because first you select the shortest one, next shortest one, next shortest one. So this selection will be uniquely, you can do it. Okay. Second one, actually if you see Prim's algorithm, In Prim's algorithm, actually, I'll just show you this simple Prim's algorithm. Suppose if you are having, say, 1, 1, 3, 4. See, in Prim's algorithm, you start at a vertex. Then you are going to create a cut. Cut means the one which separate this vertex selected from the remaining vertices. Now, this cut, there are some edges crossing the cut. And out of that, the edge having the minimal weight will be selected. Now here there are two minimal weight edges are there. There are two minimal weight edges are there. Now the question is, which edge you have to select? Which edge you have to select? So there is a problem. There is a problem. Am I clear? But if all weights are distinct, then there will not be any problem, sir. Each time when you create a cut, there is only one least cost edge is there. That is obviously selected and your minimal spanning tree will be unique. Your minimal spanning tree will be unique. So that is the idea for this, my dear friends. That is the idea for this, my dear friends. That is the idea for this, my dear friends. For example, you see this. We can also answer next question. For example, you taken this. You please tell me which smallest edge you are going to select. Which one you select? AB you select or AC you select? You don't know which one you select, sir. You don't know which one to select because both are having same cost. So you may be selecting, for example, AB you selected. You selected AB here. Now the remaining graph is like, CD. Now AB are selected vertices, unselected vertices are remaining things. So in the Prim's algorithm, what we do? We create a cut here. Again, here also we are having minimal cost weights. Now which one you select it? If there are many small weight cost edges are there, when there is a tie, you have to break the ties arbitrarily. But here in this question, what it says, if G has unique minimal spanning tree, if for every cut of G, there is a unique minimal weight edge crossing the cut. If there is only one fellow having the least weight is crossing the cut, the minimal spanning tree will be unique. The minimal spanning tree will be unique, my dear friends. Hope you understand. Like that. Now, if you see the next question, there exists a minimal weight edge in G which is present in every minimal spanning tree, which is wrong. See, look at this, sir. I create this particular cycle with all weights 1. Now let us talk about this minimal weight fellow. Now I create a spanning tree without involving that fellow. So this fellow is saying that the minimal weight edge has to be present in every minimal spanning tree. That is not necessary. Yeah. See, there is no mention. He not mentioned anything, na? So that is also possibility. That is also a possibility. He says there exists a minimal weight edge in G which is present in every minimal spanning tree. And I show that that is wrong. It is not present in every minimal weight spanning tree. I shown it. So that is wrong. Am I clear? See, whatever may be the reason. Yes, yes. Second statement. If every edge in G has distinct weight, that we already seen, sir. So S2 is for true, whereas this is false because of this. This is false and this is true. See, this type of statement they regularly ask about spanning trees, my dear friends. Yeah. S1 is false, S2 is true. Okay, sir, I am stopping today's class here. There may be 1 or 2 questions. Okay, just go through it. The solutions are available like this. This one is interesting. So I think this is the last problem. So let me solve this. This is an interesting one. With this, I will conclude today's class. This one I will conclude. Today's class I will conclude with this. Yeah. So here we are having a weighted undirected graph. We are having a weighted undirected graph. And TB a minimal spanning tree. So we created a minimal spanning tree, sir. TB a minimal spanning tree of G maintained using adjacency list. So this T is maintained using adjacency list. This T is the graph, minimal spanning tree which is created from a graph. And this is maintained using adjacency list. So this T will be having how many vertices, sir? Suppose this is having n vertices. Then how many edges it will be containing, sir? How many edges it will contain, sir? Obviously, because it is a minimal spanning tree, it contains n minus 1. Or let us use this notation so that it is easy for us to write the solution. It contains v vertices. Then how many edges it will contain, sir? It will contain v minus 1 edges. So this particular minimal spanning tree, that is also a graph. This minimal spanning tree is also a graph. So this is maintained using adjacency list. This is maintained using adjacency list. So order v plus e. Correct? Now look here. What is happened? A new weight edge uv is added to the graph. You added, of course it is a spanning tree, but for this graph which you created a new graph. Suppose this is the minimal spanning tree you are having, sir. This is the T you are having. We are adding a new weight edge. That is, this is what is added. A new weight edge is added. Let me show you this clearly. See, this is T is this. So we created a new graph T dash by just adding a new edge to this particular minimal spanning tree. Now what is that he is asking? The worst case time complexity of determining T is still an minimal spanning tree of the resultant graph or not. Okay, by adding this particular edge, the worst case time complexity of determining if T is still an MST of the resultant graph or not. See, for minimal spanning tree graph, using adjacency list, the minimal spanning tree graph for means whether there it is forming minimal spanning tree or not, to check what is the complexity of that, my dear friends. You are checking whether there is a cycle in the graph or not. You are just checking whether there is a cycle in the graph or not. So you have to trace all the vertices and all the edges of the graph, my dear friends. Okay, you have to, from every vertex you have to see, are you reaching same vertex or not. So you have to move this entire adjacency list, my dear friends. So you have to trace this entire adjacency list. So for that you require order v plus e time complexity normally, my dear friends. Order v plus e normally. But here in this T dash we are having vertices v because you added a new edge having vertices equal to v. Adding vertices equal to e v and edges also equal to v. So the complexity would be order v plus, because number of edges equal to v, this is also order v, which is order 2v, which is nothing but order v, my dear friends. So that is the answer for this problem. So that is the answer for this particular problem, my dear friends. Hope you understand. So that is the story for this problem. So we conclude today's class here. You can try this problem as homework. 2022 questions, sir. Or let me read it out. This is also simple question only. See here, first option, let me read it out. The edge with the second smallest weight is always part of any minimal spanning tree. This may be wrong, but here consider a simple undirected weighted graph of G, all of whose edge weights are distinct. Yes, yes. A is true because all edge weights are distinct. First one is selected, second one will be selected, because with these two fellows cycle will not be formed. First and second one will be selected. Obviously A is true. Next, B option. One or both of the edges with the third smallest and fourth smallest weights are part of any minimal spanning tree. See here, all edge weights are distinct. See, what is that he is saying, sir? One of the edge weight with third smallest cost, yeah, fourth smallest cost must be present in the minimal spanning tree. See, suppose you taken minimal weight is say suppose 1, the next minimal weight is say 2, both will be selected. Now suppose the third minimal weight is say 3 and fourth minimal weight is say 4. Now if the third one is here, it will not be selected. 3 will not be selected. Then fourth one, it has to be either from here or somewhere. Definitely the fourth one will not form cycle with these three fellows. Fourth one will not form a cycle. Fourth one will be separated. Then this will be selected. Suppose first smallest weight, second smallest weight, third smallest weight. Third smallest weight is not forming a cycle. It will be selected. Suppose third smallest weight forms a cycle with first and second fellow. Third cannot be selected. In that case, fourth will be selected. If third is forming a cycle, fourth will be selected. If third is not forming a cycle, then third will be selected. So one or both of the edges. Now both of the edges means, suppose both does not form a cycle, both can be selected. Am I clear? So B is also true. Next one. Suppose S is a subset of V. S is non-empty and S is not equal to V. Consider the edges with minimum weight such that one of its vertices is in S and the other in V minus S. Such an edge will always be part of any minimal spanning tree of G. See, obviously the idea of cut here only. See, once you make a cut, selected vertices, non-selected vertices, once you make a cut, this edge which is crossing the cut having the minimal weight will be selected. That is the basic idea of this particular cut, and especially here all the weights are distinct. Definitely this also will be true, my dear friends. This also will be true because it is a cut. And finally, G can have multiple minimal spanning trees. Wrong. This is wrong. Why, sir? When all the weights are distinct, G cannot have. When all the weights are distinct, G cannot have multiple spanning trees, sir. It will have one and only one spanning trees. Therefore, this is wrong. Okay, sir. So that's all for today. Thank you. Within a half an hour, I'll give both the PDFs, discrete mathematics. Yeah, discrete mathematics as well as algorithms in my Telegram group. The group name is CS_Sridhar. Within half an hour I'll post it. Within half an hour I'll post it. Thank you, sir. Any doubts? Keep attending. Okay, sir. Thank you. Please subscribe, like and share. Thank you.